Hey, everybody. So we're going to take a look now at complex numbers. And a reasonable question to ask in a series of videos about trigonometry is what, if you know what a complex number is, then your question might be, what in the world does that have to do with trigonometry? Well, we won't see that in this video, but we will find out. There'll be a few videos on this topic, that there is a deep connection between trigonometry and complex numbers, but we'll get there. So let's just start with an introduction to what complex numbers are. And the way we start, or one way to start, is with the invention of a new number, okay? And we give this number a name. This number is I, okay? So we've invented a new number. Right off the bat, this might seem troubling, okay? But there's really no reason to be troubled by it. If you feel like, well, let me say one more thing and then I'll get into this tirade. This new number is going to start with a single property. The property is, so I is the number such that I squared equals -1, right? That's really all we need to know about I to get started, okay? Another way to say that maybe is that I is the solution to this equation. I is the solution to the equation x squared plus 1 equals 0, or more correct, if we solve this, we would say then x equals plus or minus I. Okay, just like x squared minus 4 equals 0 leads us to the solutions x equals plus or minus 2, we get plus or minus I. Okay, so that's the beginning of this, okay? So if this seems weird that we just decided to invent a new number, and this number seems to break one of our fundamental rules, right? So writing down that I squared equals -1 means I times I equals -1. Seems to break one of our rules, right? If you multiply two positive numbers together, you get a positive. If you multiply two negative numbers, you get a positive. So how are we multiplying this number times itself to get a negative? Because it's either got to be positive and then it's two positives, or negative and then the product should be positive. Well, that's the problem. It's not negative, it's not positive. It's a new kind of number. It doesn't fit into that category, okay? That probably seems even stranger. And if that's the case, you're in good company. People argued about this, mathematicians argued about this when the idea of complex numbers was being introduced. Just like they argued about the introduction of 0, the introduction of fractions, the introduction of negative numbers, the introduction of rational numbers. None of those things seemed obvious to people that they should be part of our numbers when they were first introduced. So it's not uncommon for this to happen, right? Maybe a better question about whether or not we should be able to invent new numbers is this new number we invented useful? And it turns out this number is fantastically useful, okay? It takes a while to get to the applications of this. We won't be able to see much of that in this series of lectures, though I'll try to hint at some things. Suffice to say, it shows up in all kinds of applications. A couple really prime examples in my mind are electrical engineering, which I don't know too much about, but I understand that mapping a lot of things requires complex numbers. And the same thing with quantum mechanics, that having complex numbers makes descriptions of some phenomena in the quantum world, if not possible, at least easier, right? There's probably always alternate routes to these things, but these complex numbers make it a much simpler route. Okay, so what do we need to know about this number I? Well, we'll get to some geometric interpretations later. For now, let's start with some algebraic properties, okay? So in most ways, other than this one that we've described here, it behaves like under other numbers. For instance, I plus I equals 2I, right? You take a thing, you add it to yourself, you get 2 of it. Or I minus I equals 0. We already know what I times I is. I divided by I will be 1, so on and so forth, right? So it behaves very much like other numbers. It has this extra property to it, right? We can't compare it in the usual way in size to other numbers. Like I said, it's not negative or positive. It doesn't sit on that number line that we often imagine. We'll get to that kind of stuff later. What we usually do is combine it with real numbers to make, this is what we really call complex numbers. A complex number is a number, I'll call it Z, of the form Z equals X plus I, Y. Okay, so X and Y, or X and Y, are real numbers, right? The regular old numbers that we are used to, okay? Don't let the names real and imaginary, so sometimes we call I an imaginary number. Well, let's get to that part now. They'll make that statement. We call X the real part of Z, and we call Y the imaginary part of Z, okay? So a couple of things. Like I started to say, don't let the names real and imaginary lead you to believe that there's sort of a hierarchy or something like that, or that these imaginary things are imaginary or not real. I would say that they're useful, and that's real enough for me. They're important enough for me. They're useful. They're just names that have stuck. Okay. The other thing is Z is a single number. Okay, it's built out of these two parts, but it's not. We still think of it as a single thing, right? And geometrically, in later videos, we'll see that we can think of it as a single point, and that's maybe will make this come together a little bit. Okay, Z is a single number, even though it has these two parts to it. Okay, let's just write a couple of examples out. I could write the imaginary number 3 minus 7i, right? So this has the real part 3, the imaginary part -7. Okay. We could also do something like, if we're dealing with complex numbers, we might have the number 3. This is the imaginary number with the real part 3 and the imaginary part 0, right? So in reality, I could think of this as plus 0i, or I times 0. Okay, but we often don't write that when there's a 0 there, especially if everyone knows if we're dealing with complex numbers and we only see one part, we assume the other part is 0. Same thing in the other direction. If I have the number -i, this has the real part, real part 0 and the imaginary part -1. Because again, I could think of that as 0 minus I. Also notice the imaginary part is not the I, it's the coefficient of I, right? It's just how much of that imaginary number I, our new number I, do we have, the root of -1. Okay, so let's do some more algebra with these. Let's look at some of our operations. So let's be a little more formal with these examples I gave. Let's give them names. So I'm going to call z equals 3 minus 7i. And I'll use w to be what the other one was, 2 plus 5i. Okay, so I want to see what happens when we add, subtract, multiply, and divide these numbers, okay? Just to get some basic familiarity with these. So let's look at z plus w. Okay, this is going to be 3 minus 7i plus 2 plus 5i. So all of our rules of algebra still apply to these things, right? So one of our rules is we have the associative and commutative properties. And what this really tells us is that we can change the order of these things, right? Or that it doesn't matter if, right? So something like this, a plus b plus c is the same as a plus b plus c. I can change these groupings. So in this case, what I'm going to do is I'm going to lose the groupings, and then use the commutative property to change the ordering of this. I'll have 3 plus 2 minus 7i plus 5i. Oops, that's a plus. Okay, so 3 plus 2 we know how to do. That's 5. Well, let's go through a little bit of a process here. This, I can factor out this I, and I've got negative 7 plus 5. So this is 5 plus I times negative 2, which we would usually write as 5 minus, minus 2i. Okay, right, so a couple things. I know that when we define them, I wrote z equals x plus iy, and that's typically how people write it. When we have actual numbers, we tend to write I after. It doesn't really matter. That's the commutative property of multiplication. This just looks more correct to me. Notice what we got was a new complex number, right? The real part of z was 3, the real part of w was 2, the imaginary part of z was negative 7, the imaginary part of w was 5. But when we add them together, the real part of this new number, right? Maybe I could give it a name, like, doesn't really matter. Let's give it the name v. All right, this has a real part of 5 and an imaginary part of negative 2. Okay, let's look at subtraction, and then we'll generalize these two ideas. So now if we do z minus w, it's going to behave very much in the way you expect. 3 minus 7i minus 2 plus 5i. Again, I can drop these parentheses, distribute as negative. I get minus 2 minus 5i. Rearrange things, I get 3 minus 2 minus 7i minus 5i. We end up with 1 minus 12i. All right, and this is, again, this is z minus w, but it is itself a new imaginary number. Maybe I'll call it y this time. Okay, so there's our subtraction, right? So in some sense, it's generally correct to, when you're working algebraically with I, to treat it like a variable, like you would an x in an equation or something like that, right? You can combine like terms, factor it out, all those kinds of things. It's not a variable, though. It's not a symbol that stands in for some other number. It is the number itself. Okay, but it can be easier to work with it if we think of it as a variable when we're trying to do algebraic operations. But it has this one extra rule: if it gets multiplied by itself, it becomes a negative 1. Okay. All right. So those are our examples of addition and subtraction. Let's make this a little more general now. So we have a rule. So if z equals a plus bi and w equals c plus di, then z plus w equals a plus bi plus c plus di. This is going to be equal to a plus bi plus c plus di, or a plus c plus b plus di. Oops. Okay, so again, we can just shorten this. The rule looks like this. Z plus w is going to be a plus c plus b plus di, right? It's just what we did above with symbols, okay? So given, let's just copy this. So we'll have a little collection of rules over here. So given these definitions of z and w, there is our z plus w. Z minus w, again, we're just reproducing what we did. Oops, that should be a minus. What we did up above, but with symbols. So we'll have a plus bi minus c minus di. It's going to be a minus c plus b minus di. And so the result, a minus c plus b minus di. Okay, so if you look closely, what we're really doing when we add two complex numbers, we add the real parts and add the complex part, or the imaginary parts. When we subtract the real parts and subtract the imaginary parts to get our new complex number. All right, so there is addition and subtraction, pretty straightforward. Multiplication and division get a little more complicated, so we're going to handle each one on its own. They're not, oops. All right, so we're sticking with, actually, let's go back to our, let's do some examples with actual values in there, and then we'll generalize using that. So let me copy these. All right. Okay, so here's the numbers z and w. Let's multiply them. So z times w is going to be 3 minus 7i, 2 plus 5i. So now some more interesting things start to happen. Okay, so first of all, we still have our distributive laws. Okay, so we'll get 3 times 2 plus 3 times 5i plus negative 7i times 2 plus negative 7i times 5i. Okay. All right, so what ends up happening? Well, we have 3 times 2. Multiplication has that associativity and commutativity. So I can do things like, well, I've got 3 times 5i. I can think of it as 3 times 5 first and then times I. So 3 times 5 will give me 15i. Same thing here. First, I need to rearrange, though. The associativity and commutativity of multiplication means I can turn this into negative 7 times 2 times I. And this one again, or the same way, I take negative 7 times 5. And I also have an I from each, so I times I, right? This is just like you can rearrange if I've got 3 times x times 7 times y, I can turn this into 3 times 7 times x times y, or 21xy, right? We can rearrange like that. We're doing a very similar thing here. Okay, so let's see where we end up with. What we end up with. We have 6 plus 15i minus 14i plus negative 35, and then I times I, or I squared, is negative 1. Okay, and so now, what do we have? 6 plus, well, 15i minus 14i is just I. Negative 35 times negative 1 is plus 35. And now I can rewrite this as 41 plus I. So Z times W is another new complex number with the real part 41 and the imaginary part 1. Okay? So that's our multiplication. It looks a little more complicated. But if we follow the rules of algebra and we treat I like a variable, except for noting that I squared equals negative 1, right? This is a property X doesn't have. X isn't a number in this way. This is a number. Otherwise, everywhere else in here, we treated it just like it was a variable. Okay, but I cannot stress enough that it's not a variable. We'll just use that. It's like a notational trick in our head. Let it be a variable when that's useful. When it's not, we remember that it has this fundamental property that when it's squared, it's negative 1. Okay, let's generalize this rule. Okay, so let's do what we did before. We'll say Z equals A plus BI, W equals C plus DI. Then ZW is going to be A plus BI times C plus DI. This turns out a little more complicated, right? So I'm going to do everything I did here, but we won't be able to combine things, right? It was kind of nice that 3 times 2 we can write as 6. And then 6 plus 35 we can write as 41. Everything kind of collapses. We won't be able to collapse here, but we'll still get, it's still a nice illustrative formula. So using the properties, our distributive property here, we get A plus C, oh, sorry, A times C. That's how multiplication works. A times C plus A times DI plus BI times C plus BI times DI. Okay? All right, let's do a little bit of arranging. I've got AC plus, I'm going to rewrite this just subtly changing the association a little bit, ADI. I'm going to rearrange this one just like we did over here where we reordered some of the numbers, right? And I'm going to make this, I'm going to move the C between the B and the I. So we'll get BCI. And then here I'm going to move the BD together and we have an I times an I, right? So that's like this one here. Well, what do we get? We get AC. Here the I can be factored out. So we have AD plus BCI. Here we have that I squared at the end. So we get BD times negative 1. Well, let's rewrite AD plus BC times I. Instead of BD times negative 1, let's just take minus BD. Let's bring that to the front, or almost to the front. So what we end up with is that ZW is equal to, I'm going to put parentheses in here just to make things very clear. We have AC minus BD plus AD plus BCI. Right? Here's our real part of this new number. Here's our imaginary part. Okay? Not as simple as the addition formula, but not horrible, right? It takes a little bit of algebra to get there. There is a ton of interesting things locked up in this, right? This weird multiplication thing that happens where you've got these products and then there's a negative thrown in and these other sort of different products happening gives us a lot of the properties of complex numbers that we'll get to later. This is where their root is, which is all rooted, of course, in I being the root of negative 1. But this, for now, we can just think of it as a nice algebraic formula, but it does lead us to some pretty interesting, what turn out to be geometric properties of these numbers. Okay, so there is our multiplication. We're going to take a look at division. We're not going to do a ton of detail in division because we're not going to use a ton of division. But we are going to introduce one concept that makes division nice. So first, let me illustrate the problem. If I have z divided by w, 3 minus 7i over 2 plus 5i. Here's the big problem. Sorry, not the big problem. Here's a big problem. Let's go back for 1 second and let's look at something. When I did addition and subtraction, notice when I added the numbers z and w, I got a new complex number, right? It had the real part a plus c and the imaginary part b plus d. The subtraction led us to the new number with a minus c as the real part, b minus d as the imaginary part, right? In other words, it was in the right form where we have x plus y I, right? That was our definition of complex numbers. They were things in this form. I wrote I, y, and y. That order doesn't matter, right? So we want, if we have these numbers, we want to add them together and get another one of those numbers, right? That's what happens when you add real numbers to themselves. You add 2 plus 3, you get 5, right? Another number. Well, we want to make sure that when we add our complex numbers together, we get another complex number. When we subtract them, we get another complex number, right? And this shows that that works, that happens, right? We did the same thing with multiplication. We started with 2 complex numbers, and when we're done, we end up with some real number. In this case, it's AC minus BD, but that's going to be a real number, plus y times I. Again, y, AD plus BC is some real number. And so we end up with another complex number, right? We know what the real part is. We know what the imaginary part is. But looking at this, I don't know what the real part is. I don't know what the imaginary part. We can't say 3/2 is the real part, and -7/5 is the imaginary part, because this isn't the number 3/2. There's a 3 in the numerator and 2 in the denominator, but there's other stuff going on that makes it not quite that simple. Okay, same thing. This is not the same thing as having 7/5 times I or -7/5 times I, right? So what we want to do is figure out how to write this number, this fraction, in the form x plus yi. Okay, it's not even 100% clear. It's not guaranteed that that's even possible. So I want to know if it is possible. Okay, so here's a little trick I'm going to use. I'm going to multiply this thing by 1. Okay, because we know that multiplying by 1 doesn't change the value of something. So when I multiply by 1, I get the same number back, but it just might look different if the way I write 1 is clever enough. So somebody clever came up with this idea. I'm going to write 1 this way. Okay. Now, the reason I chose this way is because it's related to the denominator here, except the plus becomes a minus. Okay. Now, let's see why we wanted to do this. So let's just go ahead and use our multiplication of fractions. We'll get 3 minus 7i times 2 minus 5i. And then we have 2 plus 5i, 2 minus 5i. Okay. So I'm going to do the numerator and the denominator. I'm going to do the work off to the side. So 3 minus 7i times 2 minus 5i. I'm going to get 3 times 2 will be 6. 3 times negative 5i is minus 15i. Then I get negative 7i times 2 is minus 14i. And then negative 7i times negative 5i is positive 35i squared. Okay. So now I have 6 minus, well, 15 minus 15 minus 14 is minus 29i. The I squared becomes negative, so I have negative 35. And we get, so 6 minus 35 is negative 29 minus 29i. Okay? So there's the numerator. let's write this 3 minus 7i, 2 minus 5i. So far, nothing too surprising or useful shows up. But let's look at that denominator. Here's where something fun happens. So distributing the 2, I get 2 times 2 is 4. 2 times minus 5i is minus 10i. Then I distribute the positive 5i. 5i times 2 is plus 10i. And 5i times minus 5i is minus 25i squared. Now here's what's interesting. Minus 10i plus 10i goes away, right? Those are 0. Minus 25 times I squared is plus 25, and I end up with 29. Okay, so now notice the imaginary part of this product is 0. There's no imaginary part. Okay, so let's see what happens now when we bring this back together. The numerator we found was minus 29, minus 29i, over the denominator turns out to be just 29. Now I'm just using regular rules of algebra, right? This can be rewritten as 1/29 times negative 29 minus 29i. I can distribute that and get minus 1 minus I. And so z over w is minus 1 over minus I. That worked out pretty simply. It didn't have to. I chose these examples arbitrarily, but it worked out pretty simply unless there's an error in there. But the basic premise is correct. So this is the tactic that we use to divide, right? This is the typical way to divide when we've written our complex numbers in this form. Little preview, there are other ways to write them down that are equivalent to this, and different forms lead to different ways of doing this multiplication, division, addition, and subtraction. And some of the forms are particularly easy for doing multiplication and division. And so that's one reason we don't do this form of division that often. But it does come up, and so it's good to know. So we can write down a method for division with the following notation. If z equals a plus bi, and w equals c plus di, okay? Then we're going to define something new. We're going to define what we call the complex conjugate. Okay, so you may have heard conjugate before. I think some texts use things like the radical conjugate. So if you have a denominator where you have something like 1 plus the square root of 2 and you want to get rid of it, you have the radical conjugate 1 minus the square root of 2. You may have seen that, you may not have seen that. It's a useful little tool, this conjugate. Well, for a complex conjugate, what we mean, so we'll do the complex conjugate of z to b. We use the notation z with a bar over it. This is one common notation. There's different ones, but we use this one. And the complex conjugate just means you reverse the sign on the imaginary part. Right? That's what we did here. We took the positive, made it negative. If it was already negative, it would become positive. The important part is that they're opposite each other. The reason why is highlighted right here, right? We get these cross terms that disappear, getting rid of the imaginary part, leaving us with a fraction then, so we can get it, we can kind of remove this denominator and have coefficients, a real part and imaginary part. Okay, so then the method for division, we take z over w to be z over w, we take the complex conjugate of the denominator and multiply it I guess I don't need that. Let's just write it consistently. W, W. Okay. And I'm not going to write this one out with all of the variables a plus bi and c plus di in there, right? This is just more of a method, and then we use the multiplication we already have, and then regular algebra, right? We multiply the top and the bottom in these over on the side here, and then we just use regular algebra to get this 29 out of the denominator. Same thing here. So this just sets you up with the way to do it. You take the complex conjugate, right? In this case, it would be c minus di, and multiply the top and the bottom by that, because you're multiplying by 1 and it doesn't change the value. Okay, that is it for this one. We will find out a lot more in the next few. We're going to see that this complex conjugate has shows up in other places. There's a whole bunch of geometry behind the scenes on all of this, but we'll do that in some later videos. Thanks everybody for coming. I will see you next time.